Hello, this is Mr. Gilmore with the 7.6 Part 2 Application Problems lesson. So again, we are at the end of Chapter 7, where we're applying the information that we have learned this chapter using similarity. And in the last lesson, we saw how it was used to prove other theorems. But now today, we're just going to see it in application where dealing with certain problems, such as we are given an image of triangles, and we're trying to then find similarity between them and then use it similarity to then set of proportions or find missing side measures or missing angle measures. So where we begin with this lesson is by looking at what something's called a part-whole similarity. In other words, there's some special things that happen, especially inside triangles, where we can cut a triangle in certain ways such that the triangle that's formed on the interior of the given triangle is actually similar to the original. So let's consider the diagram below on the slide. We see triangle ABC with the segment BD cut on the interior of it. As it turns out that with this BD uniquely cutting into it, it actually forms a pair of similar triangles on the inside here. So let me point out why we have a pair of similar triangles. First off, with BD cutting in there, we are given there's a pair of equal angles. We see those clearly labeled as angle A and angle CBD. But there is actually are two triangles in here that are similar because not only do we have that one pair of equal angles, but there's a second pair of equal angles they have. It's because there's two triangles that share angle C. In other words, with two angles of one triangle equal to two angles of another, we have similarity through angle-angle similarity. Now, part of the hint that I give you is it might be helpful to redraw these two triangles. So take a look. There's the large triangle, which is angle ABC, in which we know here's angle A, here's angle B, here's angle C, and we know that this angle here is equal, and we've got angle C here. There's actually a second triangle in there that's similar to this first one. It's the part of the whole that's also similar. And where that angle is actually, or that triangle is actually angle B, because that's where that equal angle is, and angle C, again, that's where the angle is, and then point D. So as it turns out, triangle ABC and triangle BDC are actually similar to each other. So again, triangle ABC has two angles of it that are equal to two angles of triangle BDC, and they're similar by angle-angle similarity. Well, so what's really neat then is there's a unique proportion that we can pull out of this similarity. So let me dive over to the next slide here. So on this next slide, we have our same diagram, and what I've done is then I've began the extended proportion for us, okay? So we just determined that there are two similar triangles here, and we know then which side, we're then looking for which sides then correspond. So the triangles that we found earlier were triangle ABC, which was then similar to triangle BDC. Okay, so triangle ABC and triangle BDC are actually then similar to each other. So what I've done is I've picked the three sides of the smaller triangle, the one on the interior, and we're going to then match up its corresponding parts with the large triangle that we have that's similar to a triangle ABC. So we start with side BC. So side BC, as we look at our smaller triangle, is the first and third position, which means that corresponds to our larger triangle at the segment AC. And then we move on to segment DC, and DC corresponds to a smaller segment inside of our triangle, or the larger triangle, which is BC. And then BD, again, I'm starting with the second triangle and going to the first. So BD is the first and second position, and that it corresponds with the first and second position of our larger triangle, AB. So there's the extended proportion complete with all three corresponding sides of the smaller corresponding with the larger. But here's what's really interesting. Let me point this out to you. Take a look at the very first set of ratios here. Yeah, so just ignore the third ratio for right now, but take a look at the first set. Notice anything special with that? We actually are using BC twice in that proportion. BC is not only the side of the smaller triangle, but it's the side of the larger triangle as well, which is why there's some interesting things that happen, especially with this part-whole similarity. And you'll find we'll dig a little deeper into the part-whole similarity on the worksheet as well. But with this one specifically, we find that, yeah, there's actually this common side shared, and that actually gives us kind of this unique proportion where BC is used twice. So technically, there are only three values inside this proportion, and because there are only three, think algebraically, if I give you two of them, then you can then use those two to find the missing third. So let's do that. Let's do this problem now with some numbers. So what we're going to do is we're going to take this proportion with us to the next slide. Okay, so that proportion we had was that BC to AC is equal to DC to BC. Okay, that was our the proportion that we found to be special in that part-hole similarity. But now this time they give us some numbers. So we've got BC is equal to 12 and DC equals 9. We're going to find ACs. We're going to take the values that we do have and plug them in. Now notice they only gave us 2 values, but in a proportion there's 4. Well, that's because BC is used twice. We only need 2 values to find the missing third. So let's plug in what we know. BC is 12. AC is what we're looking for. DC is 9 and BC is 12 again. And now we notice that this is one equation, one variable we can solve for AC. So we're going to cross multiply. We get 9AC is equal to 12 times 12, which is 144. Divide both sides by 9, and 144 divided by 9 is 16. And there we have it. We found our missing side length. And that's what's really unique about the part-hole similarity, is that we don't need all of the information about this triangles in this case, because our proportion is unique, that we only need two values to figure out then the missing third. And really what we're leaning into here, this is kind of the what opens us up into next chapter. What we're really leaning in here when we talk about part-hole similarity is we are pushing toward the Pythagorean theorem. And we will find out that there's a unique case with part-hole similarity with the right triangle that leads us right into similarity, and that similarity then carries us into the Pythagorean theorem, and we'll see that in chapter 8. Okay, let's do another example. This one actually is from a theorem we saw on the previous lesson, known as the angle bisector theorem. And I'm going to first walk you through how to set up the angle bisector theorem proportion, and then with the values that we have up top, we'll plug in those values and then solve for our missing length. So the way the angle bisector theorem works is that when you apply an angle bisector to an angle of any triangle, it actually cuts the third side into 2 parts, and those 2 parts then are proportional to the remaining 2 sides of our triangle. So here's how I remember how to set up the proportion for angle bisector. I think of this angle bisector BM as being this kind of divider. And what I'm going to do is move from one side of the divider to the other side, and I'm going to match up the corresponding parts. So what parts actually correspond then? I'm going to choose a side of the triangle to correspond with the other side of the triangle, and then I'm going to choose a part of the third side to correspond with the other part. So the first I'm going to choose is then side AB. So my proportion looks like this. AB is a side of the original triangle, which means it needs to correspond with the other side of the original triangle. So I go to the second side, or the other side of my dividing wall here of my angle bisector, kind of that that separation there, and I go from one side to the other, and then that corresponds with the side BC. Then I set up my second ratio, which is for the parts of the triangle. So I start on my first side like I normally did, but I'm choosing the part of the third side. So my ratio is then AM to the other part on the other side of my angle bisector, which is CM. And that is how we can set up our proportion. That's how I remember it. I always remember there's the divider. I go from one side to the other, match up my side to side and part to part. And those are actually going to be proportional. That's what the angle bisector theorem proved, that this is actually a true proportion. Well, if you take a look, we're given 3 of those 4 values, which means we can find the missing fourth. We have AB as 10. We have BC or CB as 15. We have AM as 4. And we have CM, which is our missing variable. And now what we can do is cross multiply and divide. So I'm going to cross multiply here. 10 times CM is just 10 CM. Oops, let's clean that up a little bit. 10 CM. 4 times 15, that's a 4, by the way. Let's fix that. 4 times 15 is 60. And then divide by 10 on both sides. CM is equal to 6. And there we have it. Find the missing length. So the angle bisector theorem, you'll have that on your postulate theorem handout. However, it's a little bit tricky to remember how to set that proportion. Take my advice here. Use that angle bisector kind of as the dividing wall of your proportion. Go from one side to the other. Match up your side to side and part to part to form that appropriate relationship. All right, now we move into the very last set of problems here with our application problems, and that moves us into what we call indirect measurement. Now, certain lengths cannot be measured directly, meaning I'm not going to be able to get out a tape measure or a long enough ruler to measure something. And typically, a good example of this would be like, say, the height of a tall object, such as the height of a building or a lamp post, or maybe I'm even measuring something like the length of a bridge. Which we feel like maybe the measuring length of the bridge would be a lot easier because we could just kind of walk that distance. However, to actually help us then measure these really large objects, we can measure them what we call using an indirect measurement method. Because what we can do is we can set up similarity, and we can use what we know about similarity then to set up proportions and use these proportions and solve them to then find missing measurements. And what we mean by indirect measurement is we're going to be using direct measures to help set up similarity, set up that proportion, to then use direct measurements and solve for an indirect measurement. Let's take a look at an example of how we could actually set up similar triangles with finding and then using some of those triangles to find the height of a really tall object. So our example here leads us to Archimedes and the Temple of Delphi. You know, they're wondering, isn't that pronounced Delphi? Well, in Greek, it's pronounced Delphi. So we have Archimedes standing at a stark height of 6 feet 3 inches tall, where he's casting a shadow of 3 feet long. And the Temple of Delphi casts a shadow of 33 feet long. What is the height of the temple? So Archimedes is not going to get out a really tall ladder or build some scaffolding to then figure out the height of this temple. What Archimedes is going to do is using what he knows about his own height and his own shadow to set up then a similar triangle with the height of the Temple of Delphi and the shadow of the Temple of Delphi. So keep this in mind. What we'll be doing here is then I'm going to draw a picture for us. What we'll be doing is actually setting up similar triangles and then using the proportional sides of those similar triangles to solve a proportion for the missing height of our temple. Now, the first thing I want to do, though, is Archimedes is given us a height in mixed units. Let's actually convert that all into the same unit. 6 feet 3 inches is really 6 1/4 of a foot, right? 3 inches is a fourth of a foot, so I can convert that all into the same unit, 6 1/4 feet. So now let's draw a picture of Archimedes. So here's Archimedes standing tall at 6 feet, 6 1/4 foot. 6 1/4 feet tall, and he's casting a shadow of 3 feet. Now, here's a couple assumptions we're making of some sort of geometrical assumptions, and that is that Archimedes is standing perpendicular to the ground. That's the first assumption we're making. And Archimedes is casting a shadow here to the ground from his head, and that's going to form an angle there. Okay, when that shadow where the shadow is formed on the ground, there's some sort of angle then that's formed there. Okay, from the tip of his head to the end of his shadow, there's an angle formed there. Now, then we have our temple. Okay, we have our Temple of Delphi, and we don't know what its height is. Okay, we're going to find the height in feet, but we don't know what the height of that temple is right now. But that temple we do know is casting a shadow that is 33 feet long. And again, we're making a couple assumptions of the geometrical sort, which is that the temple is orthogonal to the ground, which means it is perpendicular to the ground, and that the shadow formed from the top of the temple down to where the shadow stops, it also forms an angle. And the assumption we're making is that angle of the shadow is formed identically to the angle of shadow that Archimedes casts. So what that leads us then to is to say that these two triangles are similar by angle-angle similarity. So that's really kind of the main assumption we're making of the geometrical sort. But now that we've established similarity between the two triangles, we can set up a proportion and solve for the missing height of the temple. So the proportion is, I'm going to look at this, what my corresponding sides are, would be the height of Archimedes to the height of our temple. That would be the first corresponding sides. And then we have the shadow of Archimedes to the shadow of our temple, and that is also then the corresponding parts. Well, if you take a look, we have one variable, one equation. We can cross multiply and solve. To make this a little easier on ourselves, I'm going to simplify this ratio to 1/11, right? We just divide both those by 3, and now cross multiplying is a breeze. I do h times 1, which is then just simply h, and then 6 1/4 times 11 actually gives us 68 3/4, and that unit is still in feet. And so there we have it. We've just used indirect measurement to figure out how tall our temple is based on actually measurable units. We can measure how tall Archimedes is, measure how far his shadow is, and also using a little bit of a difficulty, but we can do it, measure how long the shadow of the temple is. And then using those, we found a fourth measurement, which was an indirect measurement, something that we measured indirectly because we don't really know we don't really have the ability to get out scaffolding or a ladder to measure how tall the temple is. But there we have it, an example of using indirect measurement. And now we've actually come to the end of our lesson of 7.6 Part 2. Be sure to hop over and find that 6.2 worksheet, or 7.6 Part 2 worksheet on Canvas. And if you do have any questions on that, do not hesitate to email me. With that, be good and do good.